Since our project requires 3 integrated circuits, each for the NOT gate, AND gate, and NOR gates, I have determined that 17 pins are necessarily for NOT gates, 12 pins for the AND gates, and 11 pins for the OR gates in order to be fully operational. Consequently, we developed a diagram featuring 8 inputs along with various gates to meet the assignment requirements. This diagram includes 5 NOT gates, 5 AND gates, 3 NAND gates, 6 NOR gates, 1 XOR gate, and 1 XNOR gate.
I am here to elaborate our understanding in our Boolean expression. To get the Boolean expression of our logic diagram, first I get the expression of the gates which are directly connected to the inputs. First thing we did is make the other logic gates using only AND, NOT, and OR. First is the NOR gate, complementary of A and B. Second is the XNOR gate, C XNOR D. Then the XOR gate, E XOR F. And finally the NAND gate, complementary of GH. Let's pinpoint each gate under a corresponding Boolean expression. In the first column, A plus B, C times D, C naught, D naught, E plus F, E times F, and G times H. In the next column, A plus B naught, C naught times D naught, EF naught, and GH naught. In the third column, A plus B naught XOR CD, CD plus C naught D naught, E plus F times EF naught, complementary of EF naught times GH naught. In the fourth column, A plus B naught XOR CD, XNOR CD plus C naught D naught, complementary sum of CD plus C naught D naught and E plus F times EF naught, complementary sum of E plus F times EF naught and EF naught times GH naught. In the fifth column, A plus B naught XOR CD, XNOR CD plus C naught D naught, and complementary sum of CD plus C naught D naught and E plus F times EF naught, complementary sum of complementary CD plus C naught D naught plus E plus F times EF naught and complementary E plus F times EF naught plus EF naught times GH naught. Complementary product of complementary E plus F times EF naught plus EF naught times GH naught times EF naught and times GH naught. In the sixth column, this is a NOR gate and this is the Boolean expression. This is the NAND gate and this is also the Boolean expression. And lastly, the output Q, and it is a NOR gate and its Boolean expression is this, which serve as the Boolean expression of our whole diagram.
Hi, I'm going to present to you a short explanation of our Boolean expression on how it is simplified. So it would take us a lot of time to simplify this long Boolean expression, so we will just shorten our explanation. So first step is we use the double negation law. So a lot of changes here and removing the NOT gates at the top. And next step is again another double negation law. Change the signs of the other expressions. And in the fourth step, we've used the De Morgan's theorem and the observative law. So we compare the same expressions and we combine it into one. And in the last step, we are using the observative law, and this is our final um, expression, which is the simplified form. So if I'm going to explain this one by one, so it would take a lot of time. So here, this is just a short explanation how I simplified our Boolean expression.
So, good day, sir. In this part of this video, I'll be explaining to you the truth table as what's shown here in this screen. So, before I explain everything to you about the truth table, I'll explain to you what is truth table. A truth table is a tool used in logic, mathematics, and computer science to show all possible input combinations to a logic circuit or Boolean expression, and the corresponding output for each combination. So, what does a truth table do? A truth table systematically lists all possible combinations of input values, usually in binary, 0 or 1. 0 means low and 1 means high. The resulting output for each combination based on a logic rule or Boolean expression. So, another question will be, why use a truth table? Truth table really helps understand and analyze logic circuits or Boolean expressions, and also design digital logics, for example, in computer hardware. Then, very logic gate behavior or complex logical condition. So, for this truth table, so in this truth table, you can see here that there are 8 inputs with from column A, B, C, D, E, F, G, H. Those are the inputs. With the combinations, it will be total to 257 different inputs. So, in that case, there will be 257 combined different outputs also. So, here you can see in the truth table, you can see here from the column J, K, L, M, N, O, P, Q. These are the outputs from each different Boolean expressions. So, in these Boolean expressions, you can see it further in the logic diagram circuit that will be explained later on. So for this now, I'll show to you only the truth table from different combination of inputs together with different outputs. So as what's shown here in this truth table, the output will be highlighted as yellow color if your output will be low. But if the output will be high, it will be highlighted as red. So, for many different combinations of input, if the all inputs are low, the output will be low too. But if the all inputs are high, then output the output will be also high. So I can't explain you further along the all different kind of combination of inputs, but I can assure that as what's shown in the digital trainer in practice is very accurate as to what's shown here in this truth table. So that is for my part. Thank you so much.
And now, this is our actual circuit based on our logic design. Here we use 9 IC in total. We have 3 OR gate, 3 NOT gate, and then 3 AND gate. Here, on the left side, we have 74LS32, which is the OR gate, and then the 74LS08, which is the AND gate, and then the 74LS04, which is the NOT gate. And in the middle, we use the OR gate, and then the NOT gate, and then the AND gate. And on the left side, we have this AND gate, NOT gate, and then the OR gate, and then the AND gate. Here, as you can see, we have 8 inputs. We have input A, B, C, D, E, F, G, H, and only one output. Now, let's check some of the input and output based on our truth table. First, 0, 0, 0, 0, 0, the output is 0. And then 0, 0, 0, 0, 0, 1, the output is 0. And then 0, 0, 0, 0, 0, 0, 0, 1, 0, the output is still 0. And then 0, 0, 0, 0, 0, 0, 1, the output is 1. And then 0, 0, 0, 0, 0, 1, 0, 0, the output is 1. And then 0, 0, 0, 0, 1, 0, 1, the output is 1. And then 0, 0, 0, 0, 1, 1, 1, the output is 1. And then 0, 0, 0, 0, 1, 0, 0, 0, the output is still 1. And then we have 0, 0, 0, 0, 1, 0, 0, 0, 1, the output is still 1. Then we have 0, 0, 0, 0, 0, 1, 0, 1, 0, the output is 1. So therefore, the actual circuit is correct based on our truth table.